Download this code from codegive.com, link in the description below. OK, let's dive into Python threading with a comprehensive tutorial designed for beginners. I'll break down the concepts, provide clear code examples, and explain best practices. What is threading? At its core, threading allows you to run multiple parts of your program concurrently. Think of it like having multiple workers within a single factory, your program. Each worker, thread, can work on a different task simultaneously, potentially speeding up the overall execution. This is especially useful for tasks that can run independently or involve waiting, example waiting for network responses, reading from files. Why use threading? Improved performance especially for I/O bound tasks, waiting for external resources like network connections or file reads. While one thread is waiting, others can continue processing. Responsiveness in graphical user interfaces, GUIs, threading can prevent the GUI from freezing up when performing long-running tasks. The GUI thread handles user interactions, while other threads handle computations. Concurrency, not parallelism. In all cases, threading allows you to manage multiple tasks within a single process. Note that due to the global interpreter lock, GIL, in standard Python, CPython, true parallelism, multiple threads truly running at the same time on multiple cores, is limited for CPU-bound tasks. However, threading still offers concurrency benefits for I/O bound tasks, and libraries like concurrent.futures can bypass the GIL. Key concepts. Thread a unit of execution within a process. Process an instance of a program running in its own memory space. Concurrency the ability to handle multiple tasks seemingly simultaneously, even if they're not actually executing at the exact same instant. Parallelism the ability to execute multiple tasks truly simultaneously on multiple processor cores. Global interpreter lock, GIL. A lock in CPython, the standard Python implementation, that allows only one thread to hold control of the Python interpreter at any given time. This limits true parallelism for CPU-bound tasks in CPython. Thread safety ensuring that multiple threads can access and modify shared data without causing data corruption or unexpected behavior. Race condition a situation where the outcome of a program depends on the unpredictable order in which multiple threads access shared resources. Deadlock a situation where two or more threads are blocked indefinitely, waiting for each other to release resources. Lock, mutex a synchronization primitive that allows only one thread to acquire access to a shared resource at a time, preventing race conditions. Semaphore a synchronization primitive that allows a limited number of threads to access a shared resource concurrently. Condition variable a synchronization primitive that allows threads to wait for a specific condition to become true before proceeding. Q a thread-safe data structure for passing data between threads. The threading module. Python's threading module provides the tools you need to work with threads. Basic threading example. Explanation *. 1. Import threading * imports the necessary module. 2. Def task, name * defines a function that represents the task each thread will execute. The name argument allows us to identify which thread is running. 3. Threading.thread, target equals task, args equals 1, * creates a thread object. Target equals task, specifies the function to be executed by the thread. Args equals 1, passes arguments to the task function. Note the trailing comma, it's required to make it a tuple. For thread1.start, asterisk starts the thread's execution. This actually begins running the task function in a separate thread. 5 thread 1.join, asterisk waits for the thread to complete its execution. If you don't call join, the main program might exit before the threads finish. Output asterisk. You'll see output similar to this, the order might vary slightly due to the concurrent nature. Passing arguments to the target function. As you saw in the previous example, you can pass arguments to the function executed by the thread using the args parameter of the threading.thread constructor. Using a class for threads. You can also create threads by subclassing threading.thread. This is useful when you want to encapsulate the thread's logic within a class. Explanation asterisk. 1 class mythRead, threading.thread asterisk creates a class mythRead that inherits from threading.thread. 2 __init__, self, name, delay asterisk the constructor. Crucially, you must call threading.thread __init__, self, to initialize the base class. 3 run, self asterisk this is the method that gets executed when the thread is started. You must define a run method in your subclass. Thread synchronization, avoiding race conditions. When multiple threads access shared resources, example variables, files, you need to be careful to avoid race conditions. A race condition occurs when the outcome of the program depends on the unpredictable order in which threads access the shared resources. Using locks, mutexes. A lock, or mutex, is a synchronization primitive that allows only one thread to acquire access to a shared resource at a time. Explanation asterisk. 1 lock equals threading.lock, asterisk creates a lock object. 2 lock.acquire, asterisk acquires the lock. If another thread already holds the lock, the current thread will block until the lock is released. 3 try, finally asterisk the try, finally block ensures that the lock is always released, even if an exception occurs within the try block. This is crucial to prevent deadlocks. 4 lock.release, asterisk releases the lock, allowing another waiting thread to acquire it. Without the lock, you'd likely get an incorrect final counter value due to race conditions. Using with statement, context manager, for locks. A cleaner way to use locks is with the with statement, which acts as a context manager. It automatically acquires the lock at the beginning of the with block and releases it at the end, regardless of whether exceptions occur. Explanation asterisk. With lock the with statement automatically calls lock.acquire, at the beginning of the block and lock.release, at the end, providing a more concise and safer way to manage locks. Other synchronization primitives. Besides locks, Python provides other synchronization primitives. Asterisk threading.semaphore asterisk allows a limited number of threads to access a shared resource concurrently. Useful for limiting the number of concurrent connections to a server, for example. Asterisk threading.condition asterisk allows threads to wait for a specific condition to become true. It's often used in producer-consumer scenarios. Asterisk q.q asterisk a thread safe queue for communication between threads. One thread can put data into the queue, and another thread can retrieve it. Example using a queue, producer-consumer. Explanation asterisk. 1 q.q, asterisk creates a thread safe queue. 2 q.put, item, asterisk puts an item into the queue. 3 q.get, asterisk retrieves an item from the queue. If the queue is empty, it blocks until an item becomes available. 4 q.task_done, asterisk indicates that a previously enqueued task is complete. Used in conjunction with q.join, not used in this example, but useful for waiting until all items in the queue have been processed. 5q.put, none, asterisk puts a none value into the queue as a signal to the consumer to stop processing and exit the loop. This is a common pattern for gracefully shutting down consumer threads. Important considerations and best practices. Avoid shared mutable state. The more shared mutable state you have between threads, the more complex your code becomes and the more likely you are to encounter race conditions and deadlocks. Try to minimize shared state whenever possible. Consider using immutable data structures. Use thread-safe data structures. When you do need to share data, use thread-safe data structures like q.q. Be aware of the GIL in C Python, the global interpreter lock, GIL, limits true parallelism for CPU-bound tasks. For CPU-bound tasks, consider using the multiprocessing module instead of threading. The multiprocessing module creates separate processes, which bypasses the GIL. Or, use concurrent.futures, which can use either threads or processes depending on how it's configured. Handle exceptions carefully. Always handle exceptions properly within your threads to prevent them from crashing the entire program. Use try, except blocks and logging. Use meaningful thread names. Give your threads meaningful names using the name parameter of the thread constructor or the setName method. This makes debugging easier. Consider thread pools. For managing a large number of threads, use a thread pool, example with concurrent.futures.threadPoolExecutor. Thread pools can improve performance by reusing threads instead of creating new threads for each task. Proper shutdown. Make sure to properly shut down your threads when your program exits. Use signals, queues, or other mechanisms to gracefully terminate threads. Avoid abruptly killing threads, as this can lead to resource leaks or data corruption. Testing. Thoroughly test your threaded code to identify and fix race conditions and other concurrency issues. Example using concurrent.futures for thread pools. Example using concurrent.futures for process pools, bypasses GIL for CPU-bound tasks. Just change thread pool executor to process pool executor. Note that you will typically need to protect your main execution block with if __name __equals __main__colon when using process pools. In summary, threading is a powerful tool for improving the performance and responsiveness of your Python programs. However, it's important to understand the concepts, use appropriate synchronization primitives, and follow best practices to avoid concurrency issues. Start with simple examples and gradually increase complexity as your understanding grows. Good luck.